Hello, we are Group 3, and today we'll be talking about the RISC-V processor. Our group members are Jacob, Jama, Nestor, and Mohammed. I'll be starting us off with the short history of RISC-V and some real example of RISC-V hardware implementations from different companies. Jama will be focusing on the CPU architecture, things like cores, hyperthreading, and catching. Nestor handled the memory management side, paging and virtual memory. Mohammed will cover the instruction set architecture, including registers, sample instructions, stack management, and a sample C program with and without optimization. Altogether, we completed the picture of how RISC-V works. Hello, I'm Jacob, and this slide begins my section of the presentation. First, I'll talk about the short history of RISC-V, where it originated and why it was created. Then I'll move on to the real world RISC-V implementations, meaning the companies that actually build RISC-V processors. By covering these two areas, you'll have the background you need before we look at each company. Alright, so starting with my section, what exactly is RISC-V? RISC-V stands for Reduced Instruction Set Computer version 5, and it's basically the language a processor understands. What makes it unique is that it's open source. Anyone from a student in a classroom to a big company like Google can download the RISC-V instruction set and build their own processor around it for free. It's kind of like the Linux of processors, free, open, and community driven. RISC-V originally started at UC Berkeley back in 2010. A team led by Kristi Hasanovic and David Patterson wanted a simple instruction set that they could use to teach computer architecture. Most existing architectures were either too complex or required expensive licenses, which didn't make sense for a classroom environment. So they built their own, something clean, modern, and simple. At first, RISC-V was only meant for teaching, but the design was so good that the world quickly took notice. Kristi Hasanovic played a huge role in creating RISC-V. He's a professor at Berkeley, and he helped design the very first version of the ISA. He later became the chairman of RISC-V International, which manages the standard today. He also co-founded Sci-Fi, the first commercial RISC-V company, which we will get into later. He helped push RISC-V from a classroom project to a real industrial hardware. Now, David Patterson also played a big role. He co-invented the original RISC idea back in the 1980s, and he co-authored the official RISC-V architecture textbook. His principles and simplicity and efficiency strongly shaped the RISC-V ISA. RISC-V is basically the modern evolution of his early research. So why was RISC-V created in the first place? At UC Berkeley, researchers needed an ISA that wasn't locked behind licenses or fees. Existing ISAs were closed source and expensive, which made teaching and research harder. That's why they designed RISC-V to be easy to teach, open for research, customizable, and completely free. This freedom is the main reason why RISC-V spread so quickly. There are a few core design principles that shaped RISC-V. First, simplicity favors regularity, keeping instructions consistent, making everything clear. Second, RISC-V follows the idea of making the common case fast, optimizing what's used most. Third, smaller is faster. A lean instruction set is easier to implement and performs better. And finally, good design requires good decisions. RISC-V avoids unnecessary complexity unless it truly adds value. Together, these principles explain why universities, startups, and major companies find RISC-V easy to adopt. Even though it's been around for a little over a decade, RISC-V is already being used worldwide. Companies like Western Digital, Alibaba, Google are all using RISC-V in real products today. Billions, yes billions, of RISC-V cores have been shipped. Most of them show up in microcontrollers, IoT devices, and storage controllers. And because the ISA is an open source, it keeps evolving without waiting for one company's approval. So why does RISC-V actually matter? Before RISC-V, designing your processor was basically impossible, unless you were a huge company that could afford expensive licensing fees. But RISC-V is the first major open instruction set that means anyone can use it for free. Because there's no licensing cost, RISC-V opened the door for innovation. Universities use it to teach architecture, startups use it to build custom chips, even hobbyists can experiment with their own designs at home. It's used in IoT devices, embedded systems, and even AI hardware because it's customizable and lightweight. And today, the RISC-V ecosystem is growing faster than ever, with tools, companies, and developers all building on one open foundation. Now, shifting into the second part of my section, the hardware implementations. RISC-V itself is just the instruction set. The actual chips are made by different companies, and these chips are what we call RISC-V implementations. Each company builds different types of processors depending on what they need, whether it's low power, performance focused, or even a specialized. SiFive is one of the most important companies in the RISC-V ecosystem because it was founded by the same Berkeley researchers who created the RISC-V ISA. What makes SiFive stand out is that they design complete RISC-V processor cores that other companies can license and use inside their own chips. They offer different product families, for example, the E series, which is a low-power microcontroller, also the S series, a Linux-capable processor, and the U series, which is used for high-performance cores. SiFive has partnered with Intel, NASA, Qualcomm, and even Google. So SiFive plays a big role in taking RISC-V from an academic idea to real commercial hardware. StarFive is best known for its Vision 5 boards, often called the RISC-V Raspberry. The Vision 5 2 is one of the most affordable RISC-V boards that can run Linux distributions like Ubuntu. This is especially important for us because our class uses Ubuntu. StarFive supports Ubuntu out of the box, giving students hardware that matches the environment we learn in. In short, StarFive helps build the RISC-V software ecosystem. Western Digital is a storage company. They make hard drives, SSDs, and data center storage solutions. They rely heavily on small embedded processors inside the storage controllers. A few years ago, they switched these controllers to RISC-V, and to support that transition, they designed their own high-performance RISC-V called the Swerve. What makes this important is the Swerve core runs over 1.8 gigahertz. They're used in million storage of devices. Western Digital made Swerve open source, and their commitment shows RISC-V is reliable enough for high-volume products. When a large global company like Western Digital uses RISC-V at this scale, it validates RISC-V as industrial-grade technology. Alibaba's semiconductor division, known as T-Head, is one of the most advanced RISC-V chips designers in the world. They create the Schwante family of cores. The C906, optimized for LOT devices, C910, which runs the Linux and Android, and the C920, which is the next generation with vectors extensions for AI. These processors appear in smart devices, AI accelerators, smart TVs, robotics, and even drones. Alibaba open sourced large parts of the Schwante designs, giving developers access to high-performance RISC-V cores. T-Head showed that RISC-V can still scale from tiny devices to advanced AI workloads. These companies show the entire range of RISC-V. SiFive, which the commercial CPUs, StarFive, which develop boards, Western Digital, which storage controllers, T-Head, which has high performance in AI, inexpensive, which has ultra-low power IoT devices. This proved that RISC-V can run everything on microcontrollers and smart home devices to AI hardware and storage systems. To wrap up my section, RISC-V began at US Berkeley, built on openness and simplicity. Since then, it has grown into a global open hardware standard. Today, RISC-V implementations span everything from IoT devices, AI accelerations, and aerospace systems. Its open source nature is shaping the future of modern hardware. At this point, I'll hand it over to Jama, who will cover.
My name is Jama Rufai, and today I'm going to explain three of the most important parts of modern CPU architecture: CPU cores, hyperthreading, and caching. These three things are really the backbone of how a processor works and why computers today feel fast and smooth. By the end, you should understand how CPUs handle multiple tasks, how they run more than one thread at the same time, and how they access data quickly without slowing down. When we talk about CPU architecture, we're basically talking about how the inside of the processor is built and how it handles instructions. Think of it like the layout of the CPU. It controls how the CPU fetches instructions, how it processes them, how it moves data around, and how it manages different tasks. This includes things like the pipeline, the cores, the hyperthreading system, and the cache levels. These things work together to make sure the processor can run programs quickly and efficiently. Everything we see in modern computing, fast apps, smooth multitasking, gaming, video editing, all comes from how well the CPU architecture is designed. Understanding this gives you a better idea of what's happening behind the scenes when you're using your computer. The CPU pipeline is a really important basic concept. The pipeline is like an assembly line in a factory. Instead of doing every instruction fully from start to finish before starting the next one, the CPU breaks the process into smaller steps. These steps include things like fetching the instruction, decoding it, executing the operation, accessing memory, and writing back the result. Because the CPU overlaps these steps, it can work on multiple instructions at the same time, just each one in a different stage. This is the foundation for understanding why cores, hyperthreading, and caching actually matter. A CPU core is like a worker inside the processor. If you only have one worker, you can only work on one big task at a time. But if you have 4 or 8 workers, each one can handle different tasks or different parts of a program. Each core can run its own stream of instructions independently. That means one core can run your browser, another can handle your music, another can run a game, and so on. This is why modern CPUs feel fast, even when you have a lot of apps open. More cores don't magically make one single program faster, unless that program is written to use multiple cores, but they make the whole system smoother and more responsive. A long time ago, CPUs only had one core. The way companies made CPUs faster was just by increasing the clock speed, basically making the CPU run faster cycles per second. But eventually, companies hit physical limits. Higher clock speeds meant too much heat, which meant too much power use, and it just wasn't safe or efficient anymore. So instead of making one core faster, companies started adding more cores so the CPU could do more work at the same time. This is why almost every processor today, laptops, desktops, phones, all use multiple cores. It's a smarter way to increase performance. Instead of relying only on raw speed, the CPU gets better at handling multiple workloads. That's how we get good multitasking and smooth performance in modern systems. Hyperthreading is Intel's brand name for a technology called simultaneous multithreading, or SMT. Hyperthreading makes one physical CPU core act like 2 logical cores. These logical cores are not real physical cores, but the operating system treats them like they are. What this means is that one core can work on 2 threads at the same time. A thread is basically a smaller sequence of instructions that a program uses. Without hyperthreading, a core can only handle one thread at a time. With hyperthreading, it can juggle two threads at once. This doesn't double performance, but it helps keep the CPU busy instead of waiting around. It improves efficiency, which means the core can get more work done in the same amount of time. Inside a CPU core, there are multiple execution units, parts that do math, logic, memory access, and so on. Sometimes these units sit idle because a thread is waiting for data or waiting for a previous instruction. Hyperthreading helps fill in these gaps. When one thread is waiting, the other thread can use those execution units. So instead of wasting time, the core keeps working. It's like two people sharing the same workstation. While one is waiting, the other uses the tools. This usually gives about a 10 to 30% performance boost, depending on the program. It really helps in multitasking, productivity apps, and anything that uses multiple threads. It's one of the main reasons why modern CPUs feel smooth even when you're doing many things at once. Cache is one of the most important parts of CPU architecture. Cache is extremely fast memory located right inside the CPU. It stores data that the CPU uses often so the processor doesn't have to go all the way to RAM. RAM is much slower compared to how fast a CPU works. If the CPU had to go to RAM every single time it needed data, it would be waiting constantly and performance would drop like crazy. Cache fixes this by keeping the most important and frequently used data close to the core. There are different levels of cache: L1, L2, and L3. Each one larger but slower than the previous. This gives the CPU a layered system for accessing data quickly. Cache matters because it saves the CPU from wasting time waiting on RAM. A lot of programs repeat operations and use the same data over and over again. Cache remembers that data so it can be accessed instantly. Think of it like keeping your most important tools on your desk instead of walking to another room to get them. Every time the CPU can get data from cache instead of RAM, it saves hundreds of cycles. This makes programs run faster, shortens loading times, helps games run smoothly, and improves pretty much everything you do on a computer. When a CPU has multiple cores, each core usually has its own L1 and L2 caches. This helps each core be fast and independent. But there's also a larger L3 cache that all the cores share. This shared L3 cache helps the cores exchange data without constantly going to RAM, but it also creates a challenge. If one core updates some data, the other cores might still have an old copy in their caches. To fix this, CPUs use something called cache coherence. Cache coherence makes sure all cores see the correct updated data. It keeps everything synchronized so programs don't mess up when multiple cores use the same data. Cache coherence is just a system that keeps data consistent across all the cores in the CPU. Because each core has its own cache, they might end up with different versions of the same data. Cache coherence protocols track whether a piece of data is modified, shared, or out of date. This prevents the cores from using old or incorrect values. The main idea is that cache coherence protects the system from errors when multiple cores are working with the same memory. To summarize everything, CPU architecture is built around three key ideas. Cores let the CPU handle multiple tasks at the same time. Hyperthreading helps each core use its resource more efficiently by running two threads at once. And caching makes data access fast so the CPU doesn't waste time waiting on RAM. Together, these three features are what gives modern processors their speed, efficiency, and smooth performance. Without them, our computers would be much slower and multitasking would feel terrible.
Hello guys, my name is Mohammed, and I'll be covering the instruction set architecture, or ISA. RISC-V uses 32 general purpose registers named X0 through X31 One important thing to remember is that x0 is always 0 and you can't change it. This actually helps simplify a lot of instructions because you can use a x0 whenever you need a guaranteed 0 value. Next, RISC-V groups registers based on their purpose. The A0 to A7 registers are used for passing arguments into functions and also for returning results. The S registers S0 to S11 are called saved registers. These must be preserved by the function if it uses them. The temporary registers T0 to T6 don't need to be saved. We also have special registers like RA, which stores the return address when we call a function, and SP, the stack pointer. These two are really important for program flow and stack management. And overall, the ISA is designed to just keep everything simple and easy for the hardware to decode. RISC-V sample instructions. RISC-V has a pretty clean and simple instruction set. For example, the add instruction adds two registers, and ADDI adds a register and a immediate number. These are used constantly in basic arithmetic. For memory access, RISC-V uses LW and SW, which stands for load word and store word. In RISC-V, all memory accesses go through load/store. It's a load store architecture. For control flow, we mainly use JAL, which means jump and link. This is how functions are called. It stores the return address in RA, and then when the function is done, it uses RET, which simply just jumps back using the return address. Uh, there are also other pseudo instructions like MV for moving values or LI for loading an immediate value. These don't exist on hardware, but they make programming much easier, and assembly tools expand them into real instructions. Stack management. Now, looking at stack management, RISC-V uses a stack that grows downward in memory. So every time a function needs space for local variables or wants to save registers, it subtracts from the stack pointer. A typical function will save then the return address and any S registers it needs to use. These are called saved registers, meaning the function must restore them before returning. All of these saved values plus any local variables form what's called a stack frame. Small or very simple functions don't always need a stack frame. If they only use arguments, argument registers, and don't call other functions, the compiler can optimize away all the stack usage completely. But any bigger function will maintain a stack frame to keep everything organized and maintain the calling convention. Here's just a sample C program plus assembly. Uh, a function that just adds two integers and returns the results. When the compiler compiles this, the arguments go into registers A0 and A1. The assembly is extremely simple, and it just shows the compiler just doesn't add instruction to add the two registers and then uses RET to return. In a more detailed program or without optimization, the compiler would also create a stack frame and save registers. But because this function is so simple, the optimized version uses only one instruction to perform the calculation and then returns. This example shows how RISC-V's simplicity helps compilers generate very clean and efficient assembly code, especially when optimization is enabled. It also highlights how the calling convention and register usage work together. Overall, this just covers my section on how RSCV handles instructions registers in the stack and how the compiler turns simple C code into assembly. The main takeaway is that RISC-V is designed to be clean and easy to understand. Everything from the register layout to the stack behavior to the instruction set just follows a really simple and consistent pattern. Just seeing the code, like the C code and assembly side by side, also shows how the architecture helps compilers generate really efficient code, especially when optimizations are turned on. And this just makes RISC-V great for both learning and real world use.